Okay, so 4.2 properties of exponents and radicals. The very beginning of this is just a reminder of exponent rules, so they're written out there for you. And this is a table taken directly from Math 2. So talking about the name of the property, which is not so important to me, but how does the property work? And then just going to write in an example to refresh our memory before we move on and do more complex problems. So when I am multiplying bases, same bases with different powers, I can add the powers to come together to get a solution. So, or a product. So 2x squared times x to the fifth. Now we know x squared is x times x, and then x to the fifth is 5 more x's. So I can add my exponents, and that would give me a result of x to the seventh. When dividing bases, I can subtract my exponents. So something like x to the fifth divided by x squared. I can take the top exponent minus the bottom exponent as long as the bases are the same, and I get x to the third. If my bases are different, these rules don't apply. A power to a power, I just take and I increase my exponent by multiplying it. So x squared to the power of 5. I'm just going to do 2 times 5. Which gives me x to the 10th. Power of a product. If I have things that are multiplied inside my parentheses and I'm raising that to an exponent, I can kind of think of it as distributing the exponent, where I can multiply each part of the term to that exponent. So I can have, if I have x y to the power of 3, it's the same to write x cubed y cubed. Negative exponents is probably the trickiest of these. Whenever we're writing our answers, we're never going to leave negative exponents as an option. So this one will be used to make sure that we always have a positive exponent. For example, if I have x to the negative 3 as a result, I would rewrite that as 1 divided by x to the positive 3. A negative exponent does not give us a negative answer. A negative exponent means I need to take the reciprocal, and I get a fraction. The additional properties are really derived from the properties above, but they might just look a little bit different. And we'll be using these things today. I think this is one of the things I fixed. Hopefully yours reads that clearly and you don't have like an exponent written on top of a variable. Okay, so the product property of radicals, which really operates the same as the product property of exponents, because a radical and an exponent are the same thing, they're just written in different ways. That if I have some root of a number times a number, I could rewrite that as the root of a number times the root of a number. For example, if I have the square root of 3x, it is equivalent to write the square root of 3 times the square root of x. I can do that. I can break up my radicals and I can put them back together. Works with multiplication. It also works with division. So the next example is just of a dividing problem. The ones on the left you can see here are, right, this is radical form. And the ones on the right are on exponent form. But the concept is the same. The operation is the same. So same thing here when I'm dividing. If I were to have the cubed root of x over 5, I could rewrite that as the cubed root of x divided by the cubed root of 5. Those are little 3's in the index there. So starting off with this first set of examples should look familiar. We've done things very similar to this in Math 2, but we're adding some layers now. In Math 2, we really focus on square roots, and we barely touch on other kinds of roots, and in this class, we're going to expand that. So it says write in reduced radical form. I want no fractional or negative exponents. So just a reminder. And I'm going to work to simplify this as much as possible, and I'm going to do it in stages. I can't multiply like this first part times the second part until I get rid of the exponent. So I'm going to work on doing that first. So I'm going to leave what I have in front, 2a to the 1/3. And when I raise a power to a power, I can multiply the exponents. So I have a. Now, I don't usually write the first power here, but I'm going to use this because then I want to multiply 1 times 2/3. So I have a to the 2/3. And then b to the, now here I've got 1/2 times 2/3. So I'm just going to do that a little scratch work on the side there. Let's see. Multiply by 2, divide by 2, cancels, and I'm left with a 1/3 exponent. So So just by using that exponent on the outside of the parentheses and distributing it to the a and the b, I get 2 times a to the 1/3, a to the 2/3, b to the 1/3. But I want to combine these a's here. I want to write them together. When I multiply my bases, the rule is that I add my exponents. Oh, look, now I get fractional exponents. So on the side, I'm also going to do 1/3 plus 2/3. We did this at the beginning of the year as a review with whole number exponents. Now we just get fractions, a little more complicated. Well, these are nice because they already have a common denominator. 1/3 plus 2/3 gives me 3/3, which is just 1. So I have 2 times a to the first, b to the 1/3. Nice and simplified. And then my directions were to write in reduced radical form. Before I do the next step, are there any questions on how I combined any of those fractions? Okay, that we're going to raise the power to power and multiply. And then when I was multiplying with these, I had to add the exponents. And we can practice with operations of fractions today. So reduced radical form means I'm just going to change this now from exponent form to radical form like we practiced yesterday. So to change this from exponent form to radical form, the only one I really need to change is the b variable. And instead of b to the 1/3, this is going to become the cubed root of b. So that's just changing from exponent form to radical form. B is much of the same, except I have a quotient. So I'm going to go through and do the same similar things with my exponents. And then I'll take those exponents and write it in radical form afterwards. So I have this entire quotient, xy to the third divided by x to the 1/2, all to the power of 2/3. Since every single one of these is multiplied and divided, I'm going to take this 2/3 and I'm going to multiply every exponent by 2/3. This is x to the first, so when I multiply by 2/3, I just get x to the 2/3. And then I have y to the third. And when I multiply by 2/3, multiplying fractions, I can reduce up and down and crisscross. So that leaves me with a 2. Your calculator might also serve really handy on doing this. If you are just really struggle with fractions, you can do on your calculator 3 times 2/3. And then in the denominator, I get x to the power of 1/2 to the power of 2/3. One half times 2/3 cancels and gives me 1/3. These numbers are working out pretty nicely so far. Trying to keep it simple. I've got x's on top and x's on bottom, so I want to combine those into one thing. If you ever need a reminder, you can just go back up. Oh, when I'm dividing bases, what do I do with my exponents? Right here, I'm going to subtract. So when I've got x to the 2/3 divided by x to the 1/3, now I have 2/3 minus 1/3. So 2/3 minus 1/3 gives me another 1/3. Because the top exponent is larger than the bottom one, this will just stay on top. So I have x to the 1/3 and then y squared. So I've simplified it, and now I think the easier part is just to write it in radical form. When I write in radical form, I want to put my whole numbers first and then my radical last. Avoid writing the radical first, because right here it doesn't really, you can't really tell like where does the square root end, right? So, or where does the root end? So we'll always like write the real portion in front of the radical and leave the radical in back. So A and B are examples with variables only, and C, D, and E bring in some numbers. When I break down problem C piece by piece, I need the fourth root of 81 and the fourth root of a to the 8th and the fourth root of b to the 5th. So when I go to evaluate the fourth root of 81, if you need to plug that in your calculator, you can. But that just comes down to 3. 3 times 3 times 3 times 3 gives me 81. I'm going to start off slow, kind of like we did yesterday. Now remember, when I've got a 4 as my index, that becomes my fractional exponent. So I have a to the power of 8 over 4. Yes, I know that reduces. I'm just going to hold off a moment. And then b to the power of 5 over 4. Part of this will feel natural, and part of this is going to be a little strange. 8 divided by 4 gives me 2. My fractional exponent means that I can write this as a radical. But that's not simplified. So that's 3a squared, the fourth root of b to the 5th. But we're not done. B to the 5th we know is b times b times b times b times b. And if I'm looking for the fourth root, that means I'm taking out things in groups of 4. Oh, well, I have a group of 4. So that means that I can take one out. So that part simplifies to this. questions on C? There's going to be more of it. Pieces that need a little more explanation. All right, I'll trust you. So there's more than one path to take to do a lot of these problems. Sometimes if you take one path, it'll be the simplest, and sometimes when you take another path, you'll have to simplify them more than once. Just make sure when you get to the end that it's as simplified as can be. So for instance, this problem. I could rewrite it as the cubed root of the top and the cubed root of the bottom, or I could simplify something first. Choices. I notice that I have x to the fourth on bottom and x to the fourth on top and an x on the bottom. I'm going to choose to simplify those first. Right, so this x can cross out with one of these, and I have x to the third y squared over 125. I don't have to do that first, but it's going to make my life a little easier. Now I'm going to rewrite to focus. There's nothing else I can reduce there. I'm going to rewrite this so that I have the cubed root of the top and the cubed root of the bottom. See what you can do with this problem from there. See if you can get to the next one or two steps. Right off the bat, when I look at this problem, I notice a few things. I'm taking the cubed root of x cubed. I like that. That simplifies really easily for me. The cubed root of y squared does not, okay? And then the cubed root of 125, hopefully you can recognize that that's a perfect square. So I've kind of got three pieces going on here. Two of them are going to work out really nicely. One of them is going to not be cleared of the radical completely. So when I take the cubed root of x cubed, I can take out an x. But I can't take out the y squared because I've only got two of them on the inside. The cubed root of 125 is just 5. questions on there? All right. I'm going to move to the next one a little quicker. I feel like we've already done this problem or a similar problem to this before. So remember, you have choices here. This one's just a square root, so you've seen problems like this. You have choices here. You can simplify and then multiply and then simplify again, or you can multiply and then simplify all at once. $27 breaks down to 3 times 3 times 3. And I have another 3 on the other side. And then I've got x cubed and x squared. So I'm just going to go through when I'm doing the square root. Remember, I'm just looking for pairs. Pair of 3s, bring one out. Pair of 3s, bring one out. When I simplify, I have 9x squared times the square root of x. Simplify radical form, or reduced radical form. All right, this process of rationalizing the denominator, what this means is that I want to leave my answers with no radical in the denominator. I'm going to start off by rewriting this. So I'm just going to write the cubed root of 2x and the cubed root of 9m. Take that back. I'm going to go one step further so I don't have to write it twice. 9 is just 3 times 3m. In order to get rid of the radical in the denominator, I need to multiply by kind of what's missing. So you can think of this a little bit when we were doing our rational fractions. But here, my only goal here is to get rid of the radical in the denominator. So I want to multiply by everything here that's going to make this come out of the radical. So I'm going to choose something smart to multiply by. This is the cubed root. So in order to take out a group of something, I need 3, right? I need 3 3s, and I need 3 m's. So I'm going to multiply by what's missing. I've got 2 3s. So that means I'm going to multiply by cubed root of 1 more. I've got an m, and I want to multiply by 2 more. Whatever I do on the bottom of a fraction, I have to also do on the top. So I've created this thing that I'm going to multiply so I can just rationalize the denominator. Rationalizing the denominator means getting rid of the radical in the denominator, making the denominator rational. So if I go real slow here, what does that look like now? On the top, if I multiply that all out, I have 2 times 3 times n times m times m. Cool. I'm going to multiply that all back out in a second. On bottom, I have the cubed root of 3 times 3 times 3 times m times m times m. This is working out perfectly because I strategically picked this to multiply by. Oh, well, if I'm taking the cubed root and I have 3 3's, cool, 1 comes out. If I'm taking the cubed root and I have 3 m's, cool, 1 comes out. So the denominator here is going to be 3m. The denominator is rational. And on the top, I don't care how messy the top looks. Let's see. Cubed root of, I only got 1 2, 1 3, 1 n, 2 m's. I don't have 3 of anything. So I'm just going to write it all. Clean it up a little bit. 2 times 3 is 6. M squared, n. I don't really love how this typing came out. This is supposed to be the cubed root. If I were to write this by hand, my 3 would be like significantly lower. It'd probably be like way down here. That's just how it kind of turned out. All right, so we'll do another. Rationalizing denominator means I'm getting rid of the radical in the denominator. So I'm going to do 2 things here. 1, I'm going to rewrite this as the top, 5th root of 7, and the bottom, the 5th root of 16x cubed. Oh, I'm just going to write it all out. 16. Oh, this is going to be a little long. 16 is 2 times 2 times 2 times 2. And I can get that by just doing the factor tree. And the x cubed is x times x times x. The 5th root means I need things in groups of 5. Take a few seconds, see if you can determine what I need to multiply by so that I have a group of 5 for 2's and a group of 5 for x's. So 5th root of, I've got 4 2's. I need groups of 5, so I need 1 more. And I've got 3 x's, so groups of 5, I need 2 more. Whatever I multiply by the bottom, I'm going to multiply by the top. And now I just multiply and clean it up. On the top, I have the 5th root of 7 times 2 times x times x. There's nothing in a group of 5 I can take out of there, so all good. Now on the bottom, I could go really slow and rewrite all of this, right? Now I have 2 times 2. I've got 5 of them. You could skip this step if you're comfortable with it. And then 5 x's. Which just gives me, nope. Which just gives me 2x on the bottom. I strategically chose what to multiply the top and the bottom by so that I could get something where I could get rid of the radical in the denominator. That's what's called rationalizing the denominator. It's one of these skills where I'm writing an equivalent fraction, and the use of it doesn't really come around until we do trigonometry in semester 2. It's pretty small when I zoom out. So like radicals have the same index and the same radicand, that might be worth highlighting or starring or underlining or something to make it stand out for you. Same index. Remember, the index is the small number above and to the left of the radical. And the same radicand means the same thing underneath the radical. Only when those two things are the same can I add and subtract those radicals. At first glance, I can't add and subtract any of these. Here I have, in my middle two terms on example A, I have the same index, but my radicands don't match. And then with square root of 20 and square root of 5, I have the same index, but my 5 and my 20 don't match. So I'm going to work to simplify every one of those radicals to see if then they are like radicals. We've been practicing this. Hopefully this is something that you're comfortable with. But I'm going to give you a moment to go through and just reduce each one of these radicals. So the square root of 20, if you need to do the factor tree, go ahead and do it. Cubed root of 16, give it a try. Cubed root of 250, give it a try. The first one everybody should be able to get, no problem. The second two, give them a try. You're looking for the cubed root, so you're looking for things in groups of 3. Hopefully everybody feels pretty comfortable with the square root of 20. This is just, ooh, that's not going to work. This is just 2 square root of 5. When I look at the cubed root of 16, 16 breaks down to 2 times 2 times 2 times 2, which gives me 2. Oh, that's not a 2. Which gives me 2. And then the cubed root of 2 when I take it out. The cubed root of 250, that's 5 times 5 times 5 times 2 when you do the factor tree. So that should come out as 5 cubed root of 2. And then square root of 5 is already simplified. I just got those numbers under the radical from doing the factor tree. So I can only combine like terms when they have the same index and the same radicand. That means the little number of the radical has to match, and then whatever's underneath the radical has to match. Yeah. So I do have like terms here. 2 square root of 5 minus 1 square root of 5. Those numbers in front act as your coefficient. So 2 square root of 5 minus 1 square root of 5 is just going to leave me with 1 square root of 5. And then here I've got negative 2, 3 radical 2, plus 5, 3 radical 2. The 3 radical 2, the root 3 radical 2 are the matching parts. So negative 2 plus 5 of them, look at the coefficients, gives me plus 3 cubed root of 2. There is not necessarily a rule on which term has to go first. So if you put the cubed root of 2 term before the square root of 5, I don't think it matters.
This piece here is the like term, and then I got the coefficient in front. This piece here is the like term, and I got the coefficient in front. Next one's much the same, throw in some variables.
So I'll do 600x, and why don't you guys work on 20x and 125x? I'll do the big one. Let's see. hopefully you found that the square root of 20x reduces to 2 square root 5x, and negative square root of 125 reduces to negative 5 radical 5x. All of these are square roots, but they don't all have the same radicand. You have to have both conditions. So my like terms, bless you, 2 square root of 5x and minus 5 square root of 5x. So those are the only ones I can combine, and the other one's just going to not have anything to be combined with. 2 minus 5 gives me a negative 3 square root of 5x, and then minus 10 square root of 6x. All right, questions. We've got 2 styles of problems left. There's a lot of content in this section. A lot of practice. I don't think the concepts are hard, because sometimes when you juggle them all together, it's like, what the fuck are you doing? Answer any questions before we move on? Explain anything? You have an assignment on this today, and we will review. We'll come back to Thanksgiving. But so example 2 was basically adding and subtracting, and example 3 is going to be multiplying. All right. You really won't be asked to multiply when indexes don't match. But just to put it out there, the indices must match when I'm multiplying. Like, I'm not going to multiply the square root of 2 times the square root of 3. I'm sorry, I'm not going to multiply the square root of a number times the 2. Cool, so let's multiply. Square root of 6 times 5 is just going to be 5, 5 square root of 6. Whole number times a radical. And then the square root of 6 times the square root of 3, because they're both square roots, I can multiply those and get the square root of 6 times 3 is 18. Then just see if there's anything I can reduce. For example, square root of 6, there's nothing I can take out with square root of 18. I can. All right, so when I do the factor tree for 18, we get 3 square root of 2 when I simplify, and the square root of 6 and the square root of 2 are not like terms, so I can't combine it any further. There's no rule on which term I have to put first. All right, problem B. So distribute again. We have a whole number times a cubed root of 7. And then here, 49 times 7. You can choose to multiply these or not. I could do, this is 343, or I could keep it as 49 times 7, because really I'm going to have to factor it anyways. And for me, this is easier to factor. But it works either way. You can either multiply it and then factor it, or you could just leave it and factor it. Either way, I have 3 7s and I can take one out. Because we like to always put the radical at the end, this one I will transpose the radical in the whole number. I don't think it's a big deal if you don't, though. I'm going to change this problem on your notes. Will you change one of those to addition, please? So I'll make the change in red so it stands out. Change one of those expressions to addition. I think it'll lead better into the last example set. So I've changed problem C to be quantity 2x minus the square root of 3 times 2x plus the square root of 3. And I'm just going to multiply this all out. You could use the box here if you'd like. You don't need to. Two x times 2x. 2 times 2 is 4. X times x is x squared. 2x times the square root of 3. The 2x stays out. The square root of 3 goes on the 3 goes on the inside of the radical. Negative square root of 3 times 2x. I'm going to leave the 2x out and then the square root of 3. Negative square root of 3 times positive square root of 3 is going to give me negative square root of 3 times square root of 3 is square root of 9. 4x squared doesn't have any like terms. 2x squared of 3 minus 2x squared of 3, these are like terms, and they're going to cancel. And then minus square root of 9 is just going to give me a 3. We've talked about conjugates a few times in different integrated math courses. When I multiply something like a plus b and a minus b, something always cancels, right? That's where we get this whole difference of squares idea. And it got rid of the radical. I'm going to use that skill of finding a conjugate and multiplying by it in the next example. So these are conjugates, not to be confused with to conjugate. Woo, last example set. Here we go. Write in reduced radical form. This is all about rationalizing the denominator again. Last time when I rationalized the denominator, I'll go back. I had just a single term in the denominator. Now I have an expression in the denominator. To rationalize, I'm going to multiply by the conjugate of the denominator. My denominator is 2 plus square root of 5. The conjugate of 2 plus square root of 5 is 2 minus square root of 5. Not hard to determine. Whatever I multiply on the bottom, I've got to multiply on the top. That's how I keep fractions equal. Then I have to multiply everything on the bottom and multiply everything on the top. The top's no big deal. 2 minus square root of 5 times 1. Oh, I can do that. On the bottom, I'm going to do that in some scratch work over here. So when I multiply, 2 times 2 gives me 4. 2 times negative square root of 5 is minus 2 square root 5. Square root of 5 times 2 is plus 2 square root 5. Plus square root of 5 times negative square root of 5 is negative square root of 25. Two things happen here when I multiply by these conjugates. Minus 2 square root of 5 plus 2 square root of 5 cancels. And here I get the square root of 25, which is just 5. The denominator won't always end up being 1 or negative 1. In this case, it is. In the next problem, it ends up being like that also, but that's not always the case. I should differentiate that example a little better. Now, when I can simplify this, I'm just going to change the sign. So 2 divided by negative 1 is a negative 2. Negative radical divided by 1 is a positive radical. So I just get this as my answer. And since we're here, and since we could just change some stuff if we want to, I'm going to change problem B because I don't want it to be too similar to problem A. I'm just going to change that 2 to a 6. And hope the problem works out. Okay. I'm going to let you start it, right? Choose what I would multiply by, what would the conjugate be of the denominator, and multiply the top and multiply the bottom. And then I'll help you with the reducing part. Okay, so let's see. Maybe you're still working. Let's see how you did compared to what I wrote. So to find the conjugate, all I do is I change a minus to a positive or a positive to a minus. That's it. So the original number here was 6 that the new denominator that I chose was 6 minus square root of 3. So then I just had to multiply by 6 plus square root of 3. So I did that to the top and the bottom. When I multiply the top, I have 6 times 5 is 30, 6 times radical 3, or 5 times radical 3 is 5 radical 3. On the denominator, I multiply it all out and some things start canceling. I have positive 6 square root of 3, minus 6 square root of 3, those go away. And then a minus square root of 9, which simplifies to 3. And I end up with a 33 in the denominator. Now, if something could cancel with the 30 and the 5 and the 33, then I would simplify further. That's not the case here. It will usually not be the case, but something to check for. How'd it go? Maybe all right? That's the end of the 4.2 notes. It's a lot, but hopefully with some practice you'll be able to nail down those skills.